unyielding face of a rough planet. A rough planet exists as a testament to the universe's capacity for unforgiving extremes, a world where the environment itself is a constant, unyielding force against any semblance of fragility. Its surface, a fractured and tormented skin, speaks of a violent geological history. Towering, jagged mountain ranges claw at a turbulent sky, born from relentless tectonic shifts or colossal impacts that have scarred the planetary crust. Vast, fractured plains stretch between these peaks, perhaps littered with the debris of ancient cataclysms or carved by erosive forces far more potent than those found on gentler worlds. Deep, chasm-like valleys plunge into the planet's interior, their depths shrouded in perpetual shadow, and perhaps venting noxious gases from a restless mantle. Volcanic activity is not a mere event, but a persistent feature, with lava flows carving fiery paths across the landscape and ash plumes perpetually staining the atmosphere. The very ground underfoot would be unpredictable, prone to tremors and sudden, violent upheavals. The atmosphere of such a planet is a cruel and capricious blanket. It might be incredibly dense, crushing downwards with immense pressure, or terrifyingly thin, offering little protection from the harsh vacuum of space and the relentless bombardment of stellar radiation. Its composition would likely be a toxic brew, perhaps dominated by corrosive gases, or choked with fine abrasive dust, whipped into planet-wide storms by ferocious winds. These winds, unchecked by significant liquid bodies or complex terrain features that could temper their fury, would scour the surface, further eroding the already harsh landscape and carrying fine particulates that abrade anything exposed. The climate on a rough planet is a brutal oscillation between extremes, depending on its proximity to a star, or lack thereof. In the case of a rogue planet, temperatures could swing wildly. Days might be characterized by scorching, unbearable heat that bakes the surface and creates violent thermal updrafts, while nights plunge into an abyssal cold, capable of freezing most known substances solid. Even on a tidally locked world orbiting a star, one hemisphere would be a perpetually searing inferno, while the other remains locked in an eternal, deep freeze, with only a narrow, tempestuous twilight zone offering a slim, violent transition. Precipitation, if it exists, might take the form of corrosive acids, metallic rain, or even a superheated downpour that flash boils upon reaching the surface. Water, the familiar solvent of life, could be absent entirely, locked away as ice in the deepest, coldest pockets, or instantly vaporized by the prevailing temperatures and pressures. The constant environmental stress, from the intense radiation penetrating a thin atmosphere to the violent geological and meteorological events, paints a picture of a world actively hostile to delicate structures and complex life as we understand it. A truly rough and unyielding environment. The unyielding face of a rough planet. A rough planet stands as a stark monument to the universe's capacity for unforgiving extremes. A world where the environment itself is not merely a backdrop, but a dominant, constant, and unyielding force against any semblance of fragility. Its surface, a fractured and tormented skin, bears the deep-seated scars of a relentlessly violent geological history. Here, towering, jagged mountain ranges do not merely rise, but claw at a perpetually turbulent sky, born from the immense pressures of non-stop tectonic shifts, the explosive power of supervolcanic eruptions, or the catastrophic impact events that have repeatedly reshaped and fractured the planetary crust. Vast, desolate plains stretch like bruised skin between these brutal peaks, perhaps perpetually shrouded in volcanic ash, littered with the sharp, chaotic debris of ancient cataclysms, or relentlessly carved and sculpted by erosive forces far more potent and abrasive than any found on gentler worlds. Deep, echoing chasm-like valleys plunge into the planet's churning interior, their sunless depths shrouded in perpetual shadow and often venting noxious, superheated gases from a deeply restless and unstable mantle. Volcanic activity is not a mere intermittent event, but a persistent, defining feature of the landscape, with rivers of molten rock carving fiery, destructive paths across the surface and colossal ash plumes perpetually staining the very light that manages to penetrate the atmosphere. The ground underfoot would be a treacherous and unpredictable entity, constantly prone to violent tremors, sudden and dramatic upheavals, and the opening of new, fiery fissures. The atmosphere of such a planet is not a benevolent blanket, but a cruel and capricious shroud. It might be incredibly dense, pressing down upon the surface with immense, crushing pressure capable of flattening conventional structures, or terrifyingly thin, offering negligible protection from the harsh vacuum of surrounding space and the relentless, damaging bombardment of stellar radiation or cosmic rays. Its chemical composition would likely be a profoundly toxic brew, perhaps dominated by corrosive acids that eat away at exposed surfaces, or choked with fine abrasive dust particles whipped into planet-wide perpetual storms by ferocious, high-velocity winds. These winds, unimpeded by significant liquid bodies that could absorb their energy, or complex vegetated terrain features that could temper their fury, would scour the surface with tireless intensity, further eroding the already harsh landscape and carrying fine particulates that abrade anything exposed with the force of a sandblaster. The constant atmospheric churn could also generate colossal, planet-sized storms, swirling vortexes of unimaginable power that dwarf anything seen on more tranquil worlds. The climate on a rough planet is a brutal and often rapidly oscillating display of extremes. Depending on its orbital path and proximity to a star, or its isolated trajectory as a rogue planet adrift in interstellar space, temperatures could swing with terrifying speed and magnitude. Days might be characterized by scorching, unbearable heat that bakes the surface, melts rock, and creates violent thermal updrafts and atmospheric instability, while nights, or the permanently shadowed side of a tidally locked world, would plunge into an abyssal cold capable of freezing most known substances solid, creating vast plains of exotic, brittle ice. Even in a hypothetical twilight zone on a tidally locked planet orbiting a star, the temperature transition would be sharp, violent, and marked by perpetual raging storms born from the clash of extreme thermal gradients. Precipitation, if it exists at all within this hostile climate, might take forms utterly alien and dangerous. Corrosive acids capable of dissolving minerals, metallic rain falls as a molten or solidified hazard, or even a superheated downpour that instantly flash boils upon contact with the blisteringly hot surface. Water, the familiar and essential solvent of life on Earth, could be conspicuously absent entirely, locked away as exotic forms of ice in the deepest, coldest pockets safe from atmospheric stripping, or instantly vaporized and dispersed by the prevailing temperatures and pressures. The constant environmental stress, stemming from the intense, unfiltered radiation penetrating a thin atmosphere, the violent and unpredictable geological activity, and the extreme, often sudden meteorological events, paints a picture of a world actively and relentlessly hostile to delicate structures and complex life as we understand it. A truly rough, unyielding, and unforgiving environment where survival would be a perpetual, brutal struggle against the very fabric of the planet itself.
Welcome! Let's delve deeper into the fascinating hunt for those solitary worlds that roam the cosmos unbound by any star's gravity, the free-floating or rogue planets. Unlike the familiar planets in our solar system, these are cosmic nomads, drifting through the interstellar medium in perpetual darkness, making their detection a significant astronomical challenge. Finding them requires clever techniques that don't rely on the light of a host star because, by definition, they don't have one. The most successful strategy we currently employ to find these elusive objects is built upon the principles of gravitational microlensing, a subtle yet powerful effect predicted by Albert Einstein. Imagine a distant star, millions or even billions of light years away, serving as a luminous backdrop. As a massive object, such as a free-floating planet, drifts through space, and its path happens to align almost perfectly with our line of sight to that distant background star, its gravity warps the fabric of space-time around it. This warped space-time acts like a lens, bending the light rays from the background star as they pass by the rogue planet. This bending of light doesn't create a second image of the star that we can easily see, especially for an object as small as a planet. Instead, it causes a temporary magnification of the background star's brightness. As the planet moves into alignment with the star and then out of it, the star appears to brighten gradually and then dim back to its normal luminosity. This characteristic rise and fall in brightness over time is called a microlensing event, and the specific pattern of the light curve, how the brightness changes, provides clues about the mass of the lensing object. For a free-floating planet, which is far less massive than a star, the microlensing event is typically quite brief, lasting from just a few hours to a couple of days. In contrast, a star passing in front of another star would cause a much longer and more pronounced brightening. Detecting these short, faint blips in stellar brightness requires continuous, long-term monitoring of vast numbers of stars. Large-scale survey projects like the Optical Gravitational Lensing Experiment, OGLE, primarily using telescopes in Chile, and the Microlensing Observations in Astrophysics, MOA project based in New Zealand, have been observing millions of stars for years, patiently waiting for these rare alignment events. When a potential microlensing event is detected, other telescopes are often alerted to make follow-up observations to confirm the signal and gather more data. The challenge with microlensing is that it's a one-time event. Once the planet and the background star are no longer aligned, the magnification is gone. It's also a random process relying entirely on chance geometric alignments. This means we can't point a telescope at a specific spot and expect to find a rogue planet. We have to constantly watch large swathes of the sky and hope something drifts into view. Furthermore, microlensing primarily tells us about the mass of the lensing object. While we can infer it's likely a planet based on the duration and shape of the event, distinguishing it from a star or brown dwarf, microlensing alone doesn't give us information about the planet's size, composition, or whether it might have an atmosphere, or even moons. The scientific motivation for undertaking this challenging search is significant. The existence and abundance of free-floating planets can tell us a great deal about how planetary systems form and evolve. Current theories suggest that some rogue planets might be formed in the swirling disks of gas and dust around young stars, just like regular planets, but are then ejected from their parent systems due to gravitational interactions with other planets or the star itself. Others might potentially form in isolation from smaller clouds of gas and dust that don't coalesce into stars. By estimating how many free-floating planets exist compared to planets orbiting stars, we can gain insights into which of these formation and ejection mechanisms are most common throughout the galaxy. Estimates of the number of rogue planets vary widely, with some studies suggesting they could be more numerous than planets bound to stars. If true, this would have profound implications for our understanding of planet formation and the sheer number of planetary bodies drifting through the galaxy. Future missions, such as NASA's upcoming Nancy Grace Roman Space Telescope, are specifically designed with powerful microlensing capabilities that are expected to significantly increase our detection rate of free-floating planets, providing a much clearer picture of their population. While microlensing is the most promising avenue, astronomers continue to explore other possibilities, however speculative. Could a young, still warm rogue planet be directly imaged by extremely sensitive infrared telescopes? Perhaps, but they would be very faint and hard to distinguish from background noise. Could a rogue planet passing close to our solar system be detected by its gravitational influence on Oort cloud objects? Possibly, but such close passes are likely very rare. In essence, finding a rough planet in the sense of a starless wanderer is a testament to astronomical ingenuity, relying on the subtle ways these dark objects bend the light of more distant stars. It's a search that highlights the hidden nature of much of the universe and the powerful tools, both theoretical and observational, we use to uncover its secrets. One brief flicker of magnified starlight at a time.
Life beyond starlight. How planets without stars could harbor. Life. The conventional image of a life-bearing planet often includes a star providing warmth and energy. However, the universe may hold environments where life could flourish in perpetual darkness, on planets that roam the cosmos unbound by a star's gravity. These rogue planets or free-floating planets could potentially sustain life through alternative energy sources and clever mechanisms for retaining heat. One of the primary challenges for life on a starless planet is the lack of stellar radiation, which is the main energy source for photosynthesis and maintaining surface temperatures on Earth-like worlds. However, internal heat can play a crucial role. Rogue planets, especially larger ones, can generate significant heat through the radioactive decay of elements within their core. This geothermal energy, similar to what powers hydrothermal vents on Earth's ocean floor, could potentially sustain ecosystems based on chemosynthesis, where organisms derive energy from chemical reactions rather than sunlight. Another potential energy source is tidal heating. If a rogue planet has a moon, or is part of a binary planetary system, the gravitational interaction between the bodies can cause internal friction, generating heat. This is similar to the process that warms the subsurface oceans of some moons in our own solar system, like Jupiter's Europa and Saturn's Enceladus, which are considered prime candidates for harboring life. Maintaining a habitable temperature on a starless planet also requires effective heat retention. A thick atmosphere rich in greenhouse gases could trap internal heat, creating a warming effect that could keep a surface or subsurface environment molten or liquid. Alternatively, a thick layer of ice on the surface could act as an insulating blanket, protecting a subsurface ocean warmed by geothermal or tidal forces from the frigid vacuum of space. While the surface of a rogue planet would likely be extremely cold and dark, the interior, or a subsurface ocean, could provide a stable environment with the necessary ingredients for life. A solvent, likely water, energy, and chemical building blocks. Life in such an environment might resemble the extremophiles found in deep-sea hydrothermal vents on Earth, adapted to survive in conditions without sunlight and utilizing chemosynthesis as their primary energy source. The existence of a magnetic field could also be beneficial, shielding any potential atmosphere or subsurface environment from harmful cosmic radiation. In conclusion, while the absence of a star presents significant challenges, the potential for internal heat sources, insulating layers, and alternative energy pathways suggests that life, likely microbial, could theoretically survive and even thrive on planets that wander the galaxy in solitude. The search for such life expands our understanding of the potential diversity of habitable environments beyond those that orbit stars.
The silent wanderers exploring the realm of rogue planets. The cosmos, in its breathtaking vastness, constantly unveils phenomena that challenge our understanding of planetary formation and the very definition of a celestial body tethered to a stellar parent. Among these intriguing entities are the rogue planets, celestial nomads that drift through the interstellar void, unbound by the gravitational embrace of any star. These silent wanderers, once perhaps denizens of nascent solar systems or even born in the solitude of collapsing gas clouds, paint a compelling picture of the dynamic and often chaotic processes that sculpt the galactic landscape. Their existence, though only recently confirmed with growing certainty, opens up profound questions about the prevalence of planets beyond the familiar confines of star systems, the potential for unique environments far removed from stellar radiation, and even the faint possibility of life existing in the cold, dark expanses between the stars. The primary mechanism believed to be responsible for the genesis of these interstellar vagabonds is the turbulent dance of gravity within young planetary systems. During the early crowded epochs of stellar and planetary birth, gravitational interactions between burgeoning planets, particularly the behemoths of gas giants, can become intensely disruptive. Close encounters or resonant orbital configurations can lead to a gravitational slingshot effect, flinging one or more planets out of the system entirely, casting them adrift into the galactic sea. The sheer scale of these early interactions, coupled with the potentially large number of planets formed in many star systems, suggests that the ejection of planetary bodies might be a relatively common occurrence, seeding the galaxy with a substantial population of these cosmic exiles. However, the narrative of rogue planet origins doesn't solely rely on ejection. Another intriguing possibility lies in their formation in isolation, mirroring the birth of stars but halting prematurely. Just as vast clouds of gas and dust collapse under their own gravity to ignite nuclear fusion and become stars, smaller condensations within these clouds might also coalesce. If these protostellar embryos fail to accumulate sufficient mass to trigger fusion, they could instead form free-floating planetary mass objects. These failed stars or sub-brown dwarfs, blurring the lines between the largest planets and the smallest stars, would then embark on their solitary journeys through the galaxy, never having experienced the warmth and light of a stellar parent. The very nature of rogue planets presents significant challenges to their detection. Unlike their stellar orbiting counterparts, they do not betray their presence through the periodic dimming of a host star as they transit across its face, nor do they exert a noticeable gravitational wobble on a central star that can be measured through precise radial velocity techniques. Instead, the primary tool in the hunt for these elusive wanderers is gravitational microlensing. This phenomenon occurs when a massive object, such as a rogue planet, passes directly between Earth and a distant background star. The gravity of the intervening object acts as a lens, bending and magnifying the light from the background star, causing a brief but distinct brightening. By carefully monitoring the light curves of millions of distant stars, astronomers can identify these fleeting microlensing events and, through careful analysis of their duration and shape, infer the presence and even the approximate mass of the unseen lensing object, potentially a rogue planet. The picture that emerges from these sparse but growing detections is one of a potentially vast and diverse population of rogue planets populating our galaxy. Estimates vary widely, but some theoretical models suggest that there could be billions or even trillions of these solitary worlds, perhaps outnumbering the stars themselves. This abundance, if confirmed, would dramatically alter our understanding of planetary demographics and the sheer quantity of planetary mass objects that roam the cosmos. These detected rogue planets exhibit a range of estimated masses, from smaller than Earth to several times the mass of Jupiter, hinting at the diverse formation and ejection processes that contribute to their existence. The environment experienced by a rogue planet is starkly different from that of a planet nestled within a star system. Bereft of stellar radiation, these worlds are plunged into perpetual darkness and subjected to frigid temperatures approaching absolute zero. Their surfaces, if they possess any solid ground, are likely to be covered in thick layers of ice, formed from the freezing of any volatile compounds present. The primary source of heat for a rogue planet would be its internal geothermal activity, generated by the slow decay of radioactive elements within its core and the residual heat from its formation. This internal warmth, though significantly less than the energy received from a star, could potentially sustain subsurface liquid water oceans in some larger rogue planets, particularly if they possess a sufficiently dense atmosphere to act as an insulating blanket. The tantalizing prospect of subsurface liquid water on rogue planets raises profound questions about the potential for life beyond the traditional habitable zones of stars. While the lack of sunlight would preclude photosynthesis as we know it, the possibility of chemosynthetic life, thriving on energy derived from chemical reactions at hydrothermal vents on the ocean floor, cannot be entirely dismissed. Such life would be independent of stellar energy, drawing sustenance from the planet's internal geological processes. While the conditions would undoubtedly be extreme and vastly different from those on Earth, the sheer number of potential rogue planets in the galaxy suggests that even if the probability of life arising on any single one is infinitesimally small, the sheer volume could make the existence of such life a non-negligible possibility. Furthermore, the study of rogue planets offers a unique perspective on atmospheric science and planetary evolution in the absence of stellar influence. Some rogue planets, particularly those with significant mass, might retain substantial atmospheres, possibly composed of hydrogen, helium, or heavier molecules depending on their formation history and subsequent outgassing. These atmospheres, shielded from the stripping effects of stellar winds and radiation, could potentially exhibit unique chemical compositions and dynamic processes driven by internal heat and planetary rotation. Studying these atmospheres could provide valuable insights into the long-term evolution of planetary atmospheres in isolation. In conclusion, rogue planets represent a fascinating and increasingly important frontier in our exploration of the cosmos. These solitary wanderers, ejected from their stellar cradles or born in the darkness between stars, challenge our conventional understanding of planetary systems and the conditions necessary for planetary formation and even the potential for life. As our detection techniques become more refined and our theoretical models more sophisticated, we are beginning to glimpse the true extent and diversity of this hidden population of celestial bodies. The silent journeys of these interstellar nomads offer a profound reminder of the dynamic and often unexpected nature of the universe, constantly pushing the boundaries of our knowledge and igniting our imagination about the myriad possibilities that lie beyond the familiar glow of distant suns. The exploration of rogue planets is not just a quest to count the lonely worlds adrift in the galaxy. It is a deeper inquiry into the fundamental processes that shape the cosmos and the potential for life to exist in the most unexpected and challenging environments.